kim loại nó dày vậy nha, khi mình đặt ở nó trong điện trường cái á, thì lập tức các cái điện tích âm á, electron nó sẽ bị kéo về phía bên này. Để thầy ghi âm lại và thầy nói bằng tiếng Anh nha. Rồi thầy đưa lên page, đưa lên trang luôn.
Dạ bạn.
Okay, let's look at the properties of conductor in electrostatic equilibrium. We already knew what conductor is. Can you give me some examples for conductor? What is conductor? All of the metal are conductor, right? For example, when you have a piece of iron, of copper, aluminum, and everything, right, made from metal is a conductor. But maybe in some cases you have, for example, you take some salt and put the salt in water and you make a solution, so salt solution. Then the solution can be seen as a conductor, because when you put the two ends of the electric cord or wire into the salt solution, it can have a current through the solution. So in this case, the salt solution is a conductor too. Then when you have a piece of metal and put it in an electric field, in the very special case, let's say you have here a uniform electric field and you put a piece of metal, this one, into the electric field. So what happened to the piece of metal here? You will see that because in the metal or conductor in general, we have free charges. The free charges is the charges that can move freely inside the conductor. This is a very important and special properties of conductor. Then let's say in metal we have here electron, so the free electron will be attract to the left of the piece here and left the right side of the metal piece here with the positive charges, right? So what happened inside the metal? When we use the Gauss law inside the metal, let's say I draw a box here inside the metal, a box here, and I calculate the flux through this box. What happened? I have the box here and I calculate the flux through this box. What happened? According to the Gauss law, we don't have any charge inside the box, right? So the flux is zero. The flux is zero. So we can conclude that the electric field inside the metal is zero too. Okay, so in this case we say the field inside the metal is zero. Now what happens when we have another case? In this case we have here a piece of metal or conductor in general, and we want to calculate the electric field, and now the metal here isn't in the electric field anymore, but itself is charged. So this is the charged object. So what happened with the electric field created by this charge? You can say that when we draw a Gaussian surface like this one, you have a can. One half of the can is inside the metal, and outside the metal we have another half. Assume that the charge of this piece is positive. Then you can see that inside the metal, the electric field is zero. So you have only the electric field outside of the metal here, right? Then you can calculate the electric field at this surface. Assume that the surface is very small, so you take the charge inside this can is only A multiplied with the sigma. Sigma is the charge density at this position. So sigma multiplied with A. And here, because this is very small, so E will be perpendicular to the area. So you have the phi, the flux is E multiplied with A. So in this case, you have the flux is sigma A over epsilon 0 according to Gauss law. Then you can calculate the E. E is easily SE sigma over epsilon 0. Okay, you see here is the calculation of the flux, E multiplied with A. Here is the Gauss law, right? So you can easily find E is sigma over epsilon 0, and so on. Another example is when you have a sphere here and you have a shell surrounding the sphere, and they are concentric. It means the center of the sphere here and the center of the shell here are the same, at the same point, right? So what is the electric flux at the position here, or here, or here, or also here, right? And you can see that when, for example, when the shell is metal, then the electric field inside the shell is 0, right? What happened for the position that is outside the shell? Can you text your answer in the box? What is the electric field outside at the point that is outside the shell at the area 4? You can, for example, draw a Gaussian surface like this one. I draw a very large, and you see, I draw the surface here in the area 4, right? That is concentric with the shell. Okay, then the electric field will be perpendicular to the Gaussian surface because of the symmetry, but it is outwards or inward. Can you answer my question? Is it outward like my arrow now, or it is inward? Out or in? So what do you say? This vector or this vector? Out or in? in. Okay. Many of you answer B that the arrow must be in. Why? You are right. But why? Why? The next question. Okay, because Q in correctly. Q in here is minus 2Q plus Q will be minus Q. Negative, right? So the total charge is negative. The field must point to the center or to the charge. Okay, so I remove this one. This is incorrect. But now, what happened with the area 2? With the area 2, then I know that it will be perpendicular to the surface, right? This surface, but is it out or inwards? Okay, okay, very good. For this one, Q in is only the Q here because the minus 2Q is outside of the surface already, right? So now it's the out. And a plus here when you go inside of the chart here, right? Is it out or in? Is it out or in? Inside the sphere at the center. Out too, right? Because it's the and then when you compare this vector and this vector, which one will be longer? Which one will be longer? Can you say that immediately without any calculation? This one and this one, which one will be longer? Let's say this is the A2, okay. So you say in area 2, the above vector will be longer, right? Okay, I accept your answer, but
incorrect.
It can be wrong. It can be wrong. Why? Let's look at the result we had already here. You see, when, for example, you have the point at this distance, so smaller than A, so inside the sphere, right? And another point outside the sphere, but it can be, the electric field can be the same as this one. It is? It is? So you can see one point is out of the sphere, another point is inside the sphere, right? But the electric field can be the same, so we cannot say it without the calculation. Okay, so when I move the line here, I move the red line here, I color it in red, and you see when I move the red line up, right, you always have 2 points. It means 2 distance to the center of the sphere here. It means you have 2 points, 2 different points, but the electric field will be the same. Okay, and this is the maximum of the electric field. When you go down, you always have 2 positions, right? Even when you move down here, you can have the point here because this curve is not not only at here, right? The curve can go further to the right, to the infinity. Okay, so be careful. When I ask you that, be careful, right? So you can have 2 different positions, but you have the same magnitude of D. Do you understand what I mean?